Good evening, everyone. So I'd like to assume that the number that is available has joined, so we may as well start now. Uh, Let me share my screen quickly. All right. Uh,
Hello, Mr. Prince.
Yeah.
Okay, I thought you were talking. Sorry.
Oh, yeah. I'm here. I'm trying to get a blank PDF before we start because I say I often need that, so I forgot to get it earlier.
All right.
All right. All right. All right. I trust you can see my screen, right?
No.
All right. All right. Yesterday, I pushed out these files to compensate for the class that was missed. However, I think discussing them will do no harm. If anything, it will do some good. And then maybe at the end of this lesson, we would have completed or would have gone very far in the lesson 5 or chapter 5 of the Stallings manual. Let's get right into it. So at the end of the session, you should be able to explain how the RAM addresses are translated into cache locations, and then distinguish between direct, fully associative, and set associative. We looked at this in the last lesson. We'll just be hammering on them. And then calculate the tag, index, and offset bits for direct mapping. And then if time permits, also look at what is used to spread data from main memory into smaller parts when it comes to set associative and then associative. And also analyze the trade-offs between different mapping strategies, where it's good and where it's bad, advantages and disadvantages, basically. So let's get right into it. So these are some things that we should recall from our previous lesson: hits and miss. When data is found in the fast cache or the fastest cache, we said it is hits. So we looked at the levels of cache, and let's say we are standing on level 1 cache. If we want to find data needed for a particular processing cycle, if that data is found on the cache, it means the amount of time taken to find it will be very short. This is an advantage, and then that is described as a miss, seen as it saves the CPU processing time and then makes it function faster. And then inversely, when the data to be found is not located on the cache and it has to be addressed from a lower level, like level 2 or the RAM, it is referred to as a miss. So a level 1 miss in an inclusive memory arrangement, in a level 1 miss, level 2 is addressed, and then level 2 also addresses the RAM. In an exclusive, when the miss happens, it goes directly to the RAM and data is picked from the, we looked at this. And then locality of reference, which is the where the CPU compensates for all these for this data recovery from one point to another, trying to mitigate for the difference in speeds of the different storage system as well as their size. It uses locality of reference. And then the types are temporal locality, which deals with time. It uses the probability of a data being accessed because it was recently accessed to, gets data quickly. So for example, if I frequently address this particular data value, there's a probability that I'll take it again. Or if I have addressed it now, there's a probability I'll take it again. This means it will not be stored too far, but rather it will be kept on the cache. This becomes important due to the fact that the cache has such little storage space that you can't hold everything. Therefore, data must be prioritized. What is really needed will be stored at a time. So it uses temporal locality to store what is likely to be addressed because it has been addressed recently. So temporal deals with time. And then it uses spatial locality. It said if you use the spot, you likely need the neighbor next. And then we mentioned that in this one, if data is taken, the CPU makes guesses as to what seems like this data, what goes hand in hand with this particular data. If I take it now, there's a probability that I'll be taking this next thing. So let me take all together at once, store them in a cache at this particular time. And once I store them, if the CPU counts for this, it will count for that later. We use several analogies to describe this in the lessons previously. So if you were with us, I'm sure you understand that by now. And then here are some, okay, sorry, I'll slow down. There we are, okay. So here are some examples. If a program accesses a variable, it is likely to access it again very soon. So you see, very soon, time. Which principle is this? Is this temporal locality or spatial locality? So you may raise your hand and answer, okay? If you, or better say, you may unmute and answer. Are we dealing with temporal or spatial? Yes, Mr. Joshua.
Temporal locality.
Temporal locality. What about the next hand? Please, what do you think we are dealing with?
Yeah, I second what my brother said.
All right, thank you. So then the answer is temporal locality, but we'll see that in the next slide whether or not it's correct. Okay, this one says if a program accesses an array element, it's likely to access the next element too. Which principle is this? So this time it has taken something and it's likely to take the next thing that has a similar property within that space. So Mr. Nyako, the answer to this is
Spatial locality.
spatial locality. All right, next one. Cache memory exploits which principle to keep data ready for the CPU? So which principle does it use to mitigate for the small size of itself and then still boost speed by storing only what is needed at a particular time? What's the name of this principle? Yes, any hands? All right, so
I think it's temporal locality. Yeah. Temporal
what
locality.
about the that doesn't it also like make use of spatial locality too in this particular sense because it exploits both principles to keep data ready. In temporal locality, it takes what is likely to be accessed because it has been recently accessed. And in spatial locality, it takes what data is likely to be accessed because something common or similar to it has already been taken. In both
Oh, it's
cases, it
both.
exploits, it's both, right? Exactly. So what do we
Yeah.
call these? Yeah, what's the name, the collective name for this, what do we call it? Locality values. It's on this slide. You see, if you can spot it, you point it out. So temporal locality, spatial locality, what are they called generally?
Locality of
Loca-
reference.
Locality of reference, thank you. So the answers are temporal locality for the first, spatial, and then locality of reference for both of them. All right, so let's move on. Now here is an address problem that hammers on what we studied in the last lesson. The address problem, it says main memory, that's RAM, is very huge. Cache is tiny. We need a rule to decide where a specific block from RAM fits inside the cache. This is very important, especially when we are talking about direct mapping. Because in direct mapping, we know that each line of each block of data, right, will be thrown to a particular space inside the cache. For that reason, that space must be designated. So then the data must not end up somewhere it's not supposed to be. So then it becomes important for the CPU to recognize the data as one thing and where exactly it has to go. And even if that data is going to be broken into smaller parts, those parts must be properly known so that they can be properly sorted into the particular line where they will be stored. So in direct mapping, data is actually broken into smaller chunks. And then those smaller chunks are stored inside a line, that's the cache line. The chunks in which data is broken into when we are dealing with direct mapping are the tag, the index, and the offset. So we have the tag, the index, and the offset. The index is known as the line index. Now let's take the tag first. It says the tag identifies the specific block. The specific block. So if I go into the RAM and I am pulling out data, that data itself, its tag or the tag tells us what exactly we have taken. So the tag is what tells us what, and it also checks to see whether we have taken the exact thing that needs to be taken. So the tag is like a code derived from the data itself, from the data's bits, and it is used to identify whether or not the right data has been taken at the right time. And then there is the index or the line index. Now, when we have taken that data, we need to store it at a particular place inside our cache. The index or the line index finds the particular line, or it identifies the particular line in the cache that this particular data must go into. So you see, in direct mapping, since you're going to particular places, each one has been assigned a particular spot inside the cache. So the line index tells us which exact line inside cache that we have to go to. And finally, there is the offset. It finds the exact bytes within the line. It finds the exact byte within the line. So then as we go into the cache line, right, we look for the exact number of bytes that we need to store this particular data. So then three parts. Data is split into three parts when we are using direct mapping. So this is strictly for direct mapping. In associative and set associative, associative only takes into consideration the tag and the offset. And that's for a good reason, because we know that in associative, we are not storing in particular spots. We just store randomly, right? For that reason, there is no need to attach a particular line to a particular data value. So the index becomes irrelevant. And whereas in set associative, a new principle will be founded upon that uses a set size. So we'll be looking at that too if time permits. But for now, the tag, the index, and the offset, tag identifies the specific block, whereas the index finds the row or the line inside the cache where the data is going to be stored, and then the offset finds the exact bytes within the line for the data holding. So this is a diagram here that shows. So if we take our data and then the RAM address is given, it is broken into a tag, an index, and an offset. The index points to a particular line where data will be held. The tag tells us that this is the exact data, so it checks to see whether the data is right. Whereas the offset will now tell us, okay, inside this line, we need this amount of space inside the bytes to store the data that we have taken. So mostly in calculations, right, we calculate the offset, the index, and then whatever is left becomes the tag. We're going to look at some examples later in the slides. So now we go back to direct mapping. Let's use an analogy. So it says, the rule says every block from main memory has exactly one possible location in cache. We looked at this last time, and it says there is no choice allowed. So everybody has been assigned a position. So think of it as you are in a very strict classroom, and then the teacher has given every student a seat so that every student must sit at a particular spot. If student A comes, he must sit at desk 5. And if desk 5 is already taken, this means student A has nowhere to go. Even if desk 2 is open, he still has nowhere to go, so he is kicked out. So then, inside this particular one, there is always competition for seats. In a case where there are more numbers than seats, so if I have 5 people, let's say the class is a huge class, maybe a government school block, and they cannot afford the number of chairs for the class size. There are 20 students, there are 5 chairs. And it so happens that 3 people are assigned to 1 chair. If the first person comes and that is their seat and there's a seat open somewhere, they cannot go to that seat because their assigned seats is where they have to sit. So if that seat is already taken, maybe you came late, if that seat is taken, then walk out of the class. So in direct mapping, this is the problem. The pros, that's the advantages to it, is it's fast and easy. Since everybody knows where they're already going, there is no need to be looking for an empty cell to sit in. You either get a seat or you are kicked out. But then the cons or the disadvantages are that it has high conflict, that's the thrashing. If two popular blocks fight for the same seat. So if everybody comes and then they are supposed to take this particular seat, and then they are priority, both of them are equally important. This will mean that data will be conflicting, or the data will be fighting. Basically, the CPU will be conflicted as to which one to hold on to and which one to let go. All right. So then when we break down addresses in direct mapping, we've already looked at that. There is the tag, which holds the most significant bits, basically the part of the number that has the greatest value. And there is the line index, which points to the particular row where we are going inside the cache. Then the word offset indicates the specific word line or word within the line, indicates the specific word within the line. So the cache, that's the index length, or the what we call it, line index, is like a whole array, like a whole long row where we are going to store data. And then the word offset tells us how much of that row we need to store this particular amount of data, basically. So then the most significant bit is the tag, and then the least significant bit becomes the offset. So the smallest part of the number is the offset, largest part becomes the tag. Index is in between the two. The fully associative says you can sit anywhere. So a block from RAM can go into any empty cache line. We looked at this last week. So in a university lecture hall, there is flexibility when it comes to seats. You see, when we go for face-to-face, even though we don't do it often, when you go to the cons class, you sit where you want. I believe when we're doing this in SEM 1, you can sit wherever you find an empty seat and there are no restrictions. The trade-off is that there is the best utilization of space and there is no conflict misses. So what this means is if you go into the RAMs and into the cache, when I go to spot A and it's taken, I can easily go to spot B. But the concept is very slow, and to find data, the computer must search every single line simultaneously, and then it requires expensive hardware. Why is this difficult? So when you go into the room this time, since there are several hundred seats that you can take, you have to now scan to see which one is empty and then which one is favorable to you too. And once you identify that, you now work to that. So there is in philosophy, right? The philosophies of the days past, some of the great ones. I don't know who said this exactly, but they said that with more options comes is it more uncertainty or something. You might think that if I had more clothes, right, it will be easier for me to put on something to wear when I'm going out. But then that is what gets you, because when you have more clothes and then they are all equally nice, you are tempted to put on this one or that. Therefore, there is kind of like a conflict of interest. I don't know if I'm using this phrase right. And then you don't know which one exactly you're supposed to take because there are so many options to browse. Applying that to the cache, that is exactly what happens. So the CPU has to simultaneously at the same time browse through its entire architecture to find what's open so that it can take that. It requires expensive hardware to operate and it's very slow. So the set associative, it uses assign row. So this time you are not assigned a particular seat. Neither are you allowed to sit anywhere you want, but rather you are given a full row and you are told that if you go into this row, wherever you want to sit is fine. So you see, it combines both things, right? It combines the freedom that is given inside fully associative, despite the fact that it's limited. And then it combines that with the assignment, which is also in the direct, however, with some flexibility. So it says the analogy is in a cinema, your ticket says row 5. But when you go to row 5 and it has been assigned to you, you can sit anywhere as far as you're sitting in row 5. So if seat A in row 5 is taken, you can use B. If B is taken, you can use C. So the set associative is the best one that most modern computer systems use due to the fact that it's very, very flexible. It balances the speed of direct mapping with the flexibility of fully associative. That's that. Right, so let's compare the three methods using a visual representation. In direct mapping, as you can see, every single data here has been assigned particular spaces. So what you see here is this particular one data from memory goes directly to this side, and that's the only place it can be. This one here goes exactly here. That's the only place it can be. B2 and B3 are also assigned to particular places. So what this means is if BO is accessing this and then B3 also wants to access this, one has to leave for the other to stay. Can't have it both ways. So one fixed slot per memory block. And if you come to set associative, the cache, this is a row, and then level 0 and level 1 have both been given to particular data values. So then maybe you've been told data 0, data 2. You have been told that go to the row where there is level 0, level 1, take any empty seat and sit. So then that's a set associative arrangement. Then we have the fully associative where one data can take any space it wants. Okay, so with this particular one, I think they should have even extended more arrows to the different cache slots. So BO can go to L2, BO can go to L1, it can go to L0. CB1 same, it's just total flexibility. So here's an example concerning the direct mapping. And let's see how it works and let's understand it. And we need to remember the fact that our CPU recognizes data using bits since it deals with states, which are basically on and off. It uses zeros and ones to interpret every data you give it so that it can mimic or it can simulate that on and off in states. So since it's basically running on power, which is either on or off, it uses zeros and ones to represent that. If many data is given to you and you're supposed to put it into the cache, you need to translate it into bits. It becomes very important. So then the problem, it says that you have to map a 16 megabyte RAM to a 64 kilobyte cache using direct mapping. You are mapping a 16 megabyte RAM to a 64 kilobyte cache using direct mapping. So let's see how this works and then I'll explain it as we go. First off, we consider the cache size. The cache size has been given to be 64 kilobytes. So the first thing you want to do is convert that into bytes. Remember, converting it into bytes will mean that we'll be able to look at it in the bit form. So 2 to the power 16 bytes means we have 2, 2, 2, 2, 2. So 2 times 2 times 2, 16 times. So basically, we are going to require 16 spaces, each one holding 2 bytes, 2 bytes, 2 bytes, 2 bytes, 2 bytes, 2 bytes. So that's the idea for the 64 kilobytes. Then we come to the block size. It says, let's assume there are 4 words. The 16 bytes will be equivalent to 2 to the power 4. So mostly in the question, right, you will be given that. Mostly in the question, you actually be given that. But this one is just, so it says, let's assume there are 4 words. So then 4 words is equivalent to 16 bytes. Therefore, we have 2 to the power 4 bytes. In order to calculate the bits needed for the 3 divisions, that is our offset, our index, and our tag. We first find the offsets and then the index, and later we subtract what is left from the total bits or the total cache size, and that becomes the tag for the data. So let's map this quickly. So then it says the word offsets, that is the 4 bits. It is given as this. Is the log. So it's the log base 2 of the, what do we call it? The block size. So please take a pen and a paper, write these down, okay? There's a slide is for this particular calculation. It didn't go into detail. So put this down. The log base 2 of the block size. So whatever your block size is, log base 2 of any value that has a base of 2 itself will eliminate that base of 2 and you'll be left with the power. Right? So basically it's the power now becoming the word offset. I'll use a PDF and then I'll write on the screen and then you'll see what I'm talking about. The line index, on the other hand, is what you get when you divide the number of cache lines by the block size, by the offset, sorry. So the line index, you get that by dividing the number of cache lines by the, and then I will do examples, as I said. And finally, you get your tag by subtracting what is left. So let me just quickly show you what I mean. So please put the values down. Okay, I'm moving on to a blank PDF. It says there is the cache size, which is 64 kilobytes. And then there is the block size, which is 16 bytes. We are assuming that there are 4 words, but normally the question is to you. And there's also the word offset, which is 4 bits. We didn't know how that's going to find that right now. So just write these two down. Cache size 64 kilobytes, block size, we are assuming it's 16 bytes. And please, after you've written that, let me know so that I can move on to the PDF and demonstrate what I need to do. So please, have you written them down? Because I'm going to need you to give me what you've written down so that I can. So please, what was our cache size?
And that was 16 megabytes.
64
megabytes.
kilobytes.
64 rather, okay. The
Cache
16
size
megabytes was actually the size of the
The
RAM.
cache size was 16 cache size.
No,
Are you
64.
certain?
64
Let's
kilobytes.
see. Don't worry, it's right here. A 64 kilobyte cache right here. So the 16
Okay.
megabytes here. The 16 megabytes is actually the size of the RAM. Power out. ECG. Let's keep going. Hopefully our PC will take us to the end of it. The battery is not strong. All right. So then the cache size is 64 kilobytes. And we convert that into powers of 2 for the bits sake. So that will be 2 to the power, is it 2 to the power 4 or 2 to the power 16? It's 4. That's 16
Power
bytes.
16.
64 kilobytes is the same as 16 bytes. So that's equivalent to 2 to the power 4. So we are changing it into bytes. Remember that the bytes will become 8 bits. That's 1 byte. So we are trying to get it into bits. So we are changing the kilobyte into bytes, which is 16 bytes. And 16 bytes will be the same as 2 to the power 4. That's basically it. So basically 4 separate groups of 8 bits, something like that. 2 to the power 4. So that's the word size. Then we move on to the next one. They also asked us to the block size. It says we are assuming, and normally the question will give you the actual block size. It says we are assuming that the block size is 16 bytes. Okay. Okay, the cache size was given here to be 64, so that's 2 to the power 16. We are assuming the block size is 16 bytes, so that's 2 to the power 4. Right. Said it was 16, so then we convert that to a power of 2, that's 2 to the power 4. And then we are supposed to find our what do we call it? We are supposed to find our tag, our line index, and our offsets. A tag, our line index, and our offsets. So let's start by finding the offsets. So to find the offset, you are going to have to just use this particular formula. That's the log 2 of this guy right here. So it's log 2 of the block always. That gives you the offsets. Log 2 of the block. So if we do log 2 of something that has a base 2, the base just disappears, right? So log 2 of 2 to the power 4 just becomes 4. So it means the offset is just the power always. But that's when you're using, because it's always log 2. So it's just the power that is left. And then after we have the offset, now we can also go and find our cache, our line index. So then let's use an I for my line index. The line index's formula is also what do we call it? That's the cache size, what you have here, divided by your offsets. That's what you have here. And then finally, you log the answer you get for it. So it's the log 2 of what you have here. So we know according to the laws of indices that when you are dividing, powers subtract. So since the bases are the same, we can maintain the base and subtract the powers. So that's just going to be 2 to the power 16 minus 4. And that gives us what? 2 to the power 12. And then, as I said, you log the answer. So the formula is actually log 2 of this right here. Log base 2, like that. So then if we log this value, 2, the 2 disappears and we are just left with 12. So then that gives us the value for our, what do we call it? That. And then we also said, if you find your offset and then you find your index, whatever is left is always the tag. Whatever you find that is left is always the tag. So if we know that the total space inside the cache is 16 bytes, and then we have used 4 bytes or 2 to the power 4 bytes, basically we've used that for our offsets and we've used 12 for our index for the line, then we are just going to have to take our 16. So that's for our tag. Let me use the T for the tag. I just have to take 16 and then now I subtract my index, which is 12, and my offset, which is 4. I think I may have made a mistake somewhere that I am not noticing. Let me see. All right. Our answer can't be 0. Am I overlooking something? Let's get back to it and see. Oh, okay. So then look here. We overlooked this. That's a full data set. So the data we were taking from the onset itself had a particular space assigned to it. The data had a size, right? That size was 16 megabytes. We are overlooking it. And it should be included. So let's put that here. We take the actual data itself, its total space is 64 megabytes. And as I said, you need to convert every single thing into what do we call it? Powers of 2. So 64 megabytes is basically 2 to the power 16, 2 to the power 24. Okay, I'll give you a table for the conversions of these, but I think we know the powers of 2 a little from when we're in level 100. So it means the total space or the total amount of space that we are having to break into smaller parts is actually 64. So we've taken 4 parts out of that 64 and we are using it for our offsets. We have taken 12 parts and we are using it for our index. So for the tag, it's just going to be whatever is left, and that becomes the tag. So 64 minus 12 plus 4. And that gives us 64 minus 16. 2 to the power 24. Sorry, if we log that, what do we have? It's 24, right? So it's not actually 64, it's 24. So this side should be 24. Like so. Good. So we have 24 minus that. What does that give us? 24 minus 16. It gives us 8. Is that all right?
Yes,
And we are left
Yes,
with
8.
yes, 8. So this means our tag becomes 8. So then your final answer should be left in this format. Your tag. That's 8. And then we have our line index, which was what? 12. So you write your line index, write it in full. That's 12. And finally, we have our offsets. Let's rewrite it in full, not O. And we said the offset was what? 4, like this. So what does this mean? It means that these three things are basically the full data set we were given, but broken into smaller bits. We started out with 64 megabytes worth of data. We have brought it down to the bit level, and then we've spread it apart. We gave the line index, that's what you are seeing here. It's telling us which particular line that we are going to use to hold the data. Whereas the offset tells us how many bits we need in total to accumulate the data we have. So think of the fact that we are dealing with 2 to the power 16 inside our cache. In order to represent all these 16 bits, we will need data from 0 all the way to 1, 1, 1, 1. That's to represent all these 16. So basically a 4-bit storage space. That's what is being held here in this case. And so it's the best way I can explain it to you at this level. And then whatever is left, the tag, becomes the identifier that tells us that, okay, you've taken the correct data that is needed or you've taken the wrong data, basically. So that's an explanation for these three things. So we'll look at a few more examples too, so that we can understand it better. But if you have any questions concerning what we just worked, ask them now. In this question, we made an assumption for the block size. But in the questions, mostly it is given. Yes, Mr. Ebenezer.
Please, can you please retake this example with us again so that we get the steps well?
So help me with the values again. The RAM itself was 64 megabytes, right? So let's
Yes.
change our 64 megabytes. We need it in byte size for the sake of the 0 and 1 nature. So then 64 megabytes in bytes is equivalent to 2 to the power 16 bytes. It's a very big number actually. So 2 to the power 16 bytes. And then we have the cache size. So the RAM that we are taking, the data that we've taken, 64 megabytes, is supposed to be held inside this particular cache whose size has been given to be just 60. Is it 16 kilobytes or what? Let's see, what was it?
Yes, 64 kilobytes.
Yeah, 16
64.
kilobytes.
Okay, the RAM was 16 megabytes, and then this guy was 64 kilobytes. Cache 64 kilobytes. And then the byte representation is 2 to the power 16. This was 2 to the power 24. So let's take note, since we are using two screens, like 2 to the power 24, like so. Good. So 60 megabytes equivalent to 2 to the power 24 bytes, and then 64 kilobytes is 2 to the power 16 bytes. As I said, they are very big numbers. And we are assuming that the offsets, which will be given normally, we are assuming that this time it's a word of just 16 kilobytes. So then 16 kilobytes is equivalent to a measly 2 to the 4 bytes. So we are supposed to calculate and find out how the data will be spread. And we said in its direct mapping that the spreading is being done, we are going to need the, let me be checking the power. See, my battery is running down very fast. Actually, So then we are going to need to get our tag.
Please, I have a question.
Yeah, I'm listening, please.
Yeah, initially with the first example, I heard you saying block size.
Yeah.
So which one is the block size?
Oh, sorry. You see, I've misplaced. This is supposed to be our block size.
Our block is 16 bytes.
Yeah. And then the offset is supposed to come down here. So we are supposed to find the offsets. It's not given. Sorry. So then we have our offsets here. We'll find that. So the block size is here, 16 kilobytes. And in the question, it will be told specifically that the block size is 16 kilobytes. What this basically means is the data that we are taking from the RAM, actually, the RAM itself in totality has 24. However, if we go into the cache, we are going to need this amount of space to hold the data. Oh no, sorry, this is how much space that the cache has available to hold the data. And then the block size tells us that the data that we are carrying, this is how big it is. So the data itself coming from the 16 megabyte RAM, this is its actual size. But we are going to want you to store it inside this particular region, which is only 64 kilobytes big. So we want you to find a way to spread the data, but the data will be converted into address, right? Then some of it at least will be converted into address, whereas the tag becomes the main data itself, the most significant part of it. So then when breaking it into these respective parts, the address will now have 3 sides. So we are converting these values into an address, the offset, the line, index, and then the tag. The tag being the most significant part, which holds most of the information concerning the data and makes us verify that this is the correct data. The line we will need to hold that particular data. So we start with the offset. To calculate the offset, you will take a log to the base 2 of your block size. So our block size in this one is 2 to the power 4. So if you punch log base 2 of 2 to the power 4, you're going to get 4. Basically, the base disappears like that. And then we come to the line. In order to calculate the line index is a log to the base 2 of the quotient of your cache. So you take your cache, you divide it by the offsets, and then you find the log to the base 2 of that. That always gives you the line index. So basically, we are taking cache, and then we are going to break it into smaller regions that will fit the data that we are going to have. So that's 2 to the power 16 divided by 2 to the power 4. And then you find
Hello, Mr. Prince. Are you talking?
Ali,
Bro, I think his machine is off. I think his machine is off.
Oh, his machine is off, eh?
Yeah, I'm sure.
Alright, is it Matilda?
Oh. Yeah, how free you?
Is it Madam
His
Matilda?
machine is off. His machine
Or
is off. He
laptop
said
is
it's
going
off.
off while lecturing?
He said he has a light out, that's why.
Hey, this guy. You do ask. That will be that.
But he said the power is back. The power is back. The power is back. It's coming.
Mm. Boss, you have to.
Hello, everyone. Good evening again. Oh, it's me, Prince. My PC just went off, but the light has also been restored. So I'm turning it back on and I'm joining the session. This is my phone. Right, you see the 64% was all a facade, something that dropped from 100 to 64 in 4 minutes there. But as I'm here, I'll still be trying to use my mouth to explain to you. As a matter of fact, I think I have a software on my phone that I can use to be tutoring while my PC is trying to decide its self identity and all that. Eh. So we're trying to work out the particular address spaces for direct mapping, right? Let me see. Find this software. Yeah. Please, as we learn, in case you hear my neighbor laughing, don't mind it. That guy is not normal. Joshua, please allow me to share my screen with this account. So the PC is still getting to know itself
Sure.
better. All right. So just make me a presenter, that's all. Tap on
Allow
my
me, sir.
account. All right. Thank you. Can you see my screen?
Yeah, I can see your screen.
All right. This software, it's been a while since I opened it, so let's hope it works. Yeah, the PC is on now, so hopefully. It's been so long since I opened the software, so I don't know if it's still active. I think even the phone used to have a share board optional, so that I will directly share that. Okay, so everything is bugging. So let me just talk my way through it. The PC is still getting kickstarted. I say but the things are loading. So what I was saying was, if we take every single data that is coming from a block inside the RAM. In this one, they said the RAM was having a total space of I said the RAM. The data held in RAM at the time was having a total space of 64 megabytes. This will have to be broken into reasonable sizes that can be held by the cache. But we know that the cache is very small. 64 kilobytes as compared to 64 megabytes is basically nothing. So it will be converted into a code, and that code will hold an address. As it's being converted into a code for the code with an address, only some part of the data inside the RAM will be taken, just a little part. The part of it that is going to be taken and then used, just that small part, is going to become what we call the block, basically the block size. So the size of what we are going to take, that will become the meaningful data later, is going to become the block size. But the block size has to be converted into an address. So then the conversion of it into an address is where the offset comes in. So then log 2 of the block size gives us the offset. After doing this, we will also need to find where exactly in the cache we are going to hold the data, which line holds the data, since it's direct addressing. In order to do that, we do the cache size divided by the offset. So if I divide the cache size by the offset, the answer I get now becomes the new line index, which is the space where the data is being held. And then we find the log of that. And finally, the tag is what you get when you subtract the sum of your line index and then your offset from the total amount or the total space that was indeed or initially held by the RAM. That becomes the meaningful data that the RAM was holding in address form, basically. PC is back. So I'll be joining in a second there. Charlie, the power is gone again. Power is gone again. What's oh Charlie? CG for you. The PC is back on. The power is gone, but I don't know what kind of miracle it will pull. Currently, the battery is at 60 something, but that's the same percentage as which it dropped off the first time. But let's test our faith. If it can give us just 15 minutes, I think we can do a lot. This is why I like moving fast too.
What's the idea? Just relax, okay? My 80s machine is still loading. Doesn't go off before it finishes loading. Yeah. Okay. So here's what I'm going to do. Let's solve these questions concerning the block size and whatnot to explain what I was detailing right now better. So let's take the first one. This one says, let's do direct mapping. We are mapping a 16 megabyte RAM to a 64 kilobyte cache with a block size of 16 bytes. So then this is the RAM, this is our cache, this is our block size. So let's convert all these into what do we call it? Let's start with 16 megabytes. If we convert this into bytes, what are we going to have?
Two raised to the power 24.
The power 24. Then we have our cache. And that's 64 kilobytes. Let's move very fast because this PC is not dependable. If we convert that, what are we going to be having? It's 2 to the power 16, right?
16. Yes.
Good. And then we have our 16 bytes for our block size. And that's just going to be 2 to the power 4. Good. So let's convert this into their necessary addresses quickly. So what do we need? We need our offsets, we need our line index, and then we need our tag. So let's just find the offsets and then the index, and then the tag will find itself after we subtract. So then our offset is going to be the log is 2 of our block size, which is 2 to the power 4. And then if you pound that to a calculator, what are you getting? 4. And then our index, on the other hand, is going to be the log is 2 of our, what do we call it? Cache size, which is 64, basically 2 to the power 16.
Over block size.
Yeah, over block size. We're following, that's good. 2 to the power 16 divided by our block size, which is 2 to the power 4. And then that will be 16 minus 4. The bases stay the same. So basically 2 to the power 12. And then if we do log 2 of that, we'll be left with just the 12. The 2 disappears. And finally, the tag is going to be the available total available, what do we call it, bytes for the data we're holding, which was 24, without the path that has been assigned to the offset, and then the path that has been assigned to the line index. So 24 minus all that. That's just going to be 24 minus 16.
Minus 6.
And that gives us 8. So this, Mr. Nyako, I believe this, when you said we should resolve it, this one explains it, right? Let's move fast. That's it. Nyako Ada. Ada. Okay. Right. Let's look at the next question too. So please have your parameters down. We are going to have to convert all we see into what do we call it? Bits. Someone can be doing that for us. We have this one, direct mapping 32 megabyte RAM to a 128 kilobyte cache with block size 32 bytes. So if 16 megabytes is 2 to the power, what do we call it? 24. Then 32 is going to be what? 2 to the power 25, right?
Yes, yes.
Good. So then if we start with our RAM, that's going to be 2 to the power, so 32. 32 megabytes is 2 to the power 25, like so. And then our 128 kilobytes. So if 64 is half of 128, and then the 64 is equivalent to 2 to the power 16, that will be 2 to the power 17. So 128 kilobytes is going to be 2 to the power 17 bytes. And then finally, if our 16 bytes is 2 to the power 4, then 32 is going to be 2 to the power 5. All right, so then with that in mind, let's take our offset. Our offset is the log of 2 to the power 5, right, for the block size. So the log 2 for the block size. And then we know that will just give us 5. But when you're working this, you just show log 2 to the power blah blah, and then you do it. Our index, on the other hand, is going to be the log 2 of our cache size, which is 2 to the power 17. So that's 17 divided by our offsets, which is 2 to the power 5, which is 5. Okay, so 17 minus what do we call it? 5, that's 2 to the power what? 12, right? And we log that and we are left with what? Just 12, like that. And then the tag is going to be 5 plus 12. And we subtract all that from the total amount of space that we started out with, which was 2 to the power 25, a log of that, which is just 25. So if we subtract all that, 5 plus 12 is 17, right? So 25 minus 17, and what does that give us? 8. So notice something, some things might have remained constant, right? Some things might have remained constant. I think the tag in this question remain constant. There's actually a relationship that the indexes share sometimes depending on the way the numbers change, but the tag is just dependent on the values for every single data is independent. So it changes. The tag will mostly change. Let's move on to this one, or let's do something that is a little different. So it says we are mapping a 32 megabyte RAM with a block size of 32 bytes, but then it doesn't give the cache size. So let's make an assumption that the cache size is still, we can make any. So which one should we use here? And then you attempt it and tell us what the answer is. So this time we are mapping a 32 megabyte RAM, block size of 32 bytes. Let's assume that the cache size that we are dealing with is something like, let's say, maybe yes, 256. So 256 kilobytes. So this is our cache size, okay? Assuming our cache size is 256 and then our block size is this, can you tell me what exactly our tag, our index, and then our, what do we call it, offsets will be for this data? This, okay, yes, it's basically the same as what we just did, right? Just that the only change is the 256 kilobytes. So if 128 kilobytes is 2 to the power 17, then 256 is going to be 2 to the power 18, right? So we'll use that. The PC is gone again, but the phone is fully active. ECG4. Okay, so you hang on. As you work it, let me see if I can download. I know our time is up, but if I can download a whiteboard software. Yeah. So here's one. So the question we're doing, please, can you see my screen? Please affirm if you can see my screen.
Yes, I can see your screen, sir.
So we started with our RAM. And we know that the size of the RAM is what? 32. So in bytes, that's 2 to the power 5. And then we also checked our cache size. That is 256, which is equivalent to 2 to the power 18. So this 2 to the power 25 is 2 to the power 18. And then we have our, how much they give us for our block size?
64.
Was it 4?
Oh.
Was it 16 or 64?
64, I guess. Or maybe they confirm.
So please, those who took notes of the screen at the time.
I saw 64.
That's for the block size. Okay.
Yeah.
64 bytes. So 264 bytes is equivalent to
The block size is 32 bytes. The one you
32
asked us
bytes.
to solve is 32 bytes.
No, that one, the RAM was 32. Oh.
Almost 32 megabytes.
Yeah, so the block size was 64. That's what I saw.
It was 64. Okay. So 64 bytes. Is it 64 bytes or kilobytes?
kilobytes.
Okay, if it was really 64 kilobytes, then that would mean 2 to the power 16. Oftentimes, the block size is given in bytes, though. The block size is often given
And
in.
then please confirm.
The file is on the PC. PC has gone off, so now I'm on mobile. So we are going by our guts here.
So I have a screenshot of it.
That's powerful.
And
So please, quick.
RAM is 32 megabytes and block size is 32 bytes.
Bytes.
Oh,
So
okay,
block
okay.
size is bytes. All right, thank you. But then the 32, what do we call it? This side was 256. Yes, so that's 2 to the power 18. So I guess that's legit. All right, so please, are we working?
Yes, so I am getting, or I should wait.
Oh, no, yeah, you can share.
So I'm getting tag to be 7, index 13, and then offset 5.
All right, index 13. He says his offset is 5.
That's the same answer, sir.
All right. I know the software. The software you can't clean up. I don't know who designed it. Charlie, as IT students, when we are designing things, let's check this when we grow. Keep your data in mind and all these things too. And let's work it and see. And then we are going to end on this note. I think this was the last thing we were to look at in that particular lesson. Even though I wanted us to look at the follow-up lesson that will finally conclude the entire chapter 5. I think we've at least we've learned something new. So we find our offsets, then we find our index, and then we find our tag. So let's start with the offset. The offset is log 2 of our index, log 2 of our box block, and then the block was given to be what? 2 to the power. What did we get for the block? Was it 2 to the power 5? Yes. So that's just equivalent. 5. Good. And then we take our index, which is the log 2 of the cache. And what was the cache size? 2 to the power what?
18.
18.
2 to the power 18 all over 2 to the power 5 for the block. Good. So 18 minus 5 gives us 13. So 2 to the power 13, and you log 2 of that, you'll be left with 13. So then the tag becomes the total space that was available from the start. That was 2 to the power what?
225.
2 to the power 25. We log that to get 25, and then we subtract the sum of these two. That's 5 plus 13, that's 18. And 25 minus 18 indeed gives us 7. So then we will write it as our tag. That's the most significant bit always. So tag. And then sometimes you'll be asked to represent it in bits too. So I believe you know how to do that already. But we start the tag here. That is going to take 7. And then we are going to have our index, our line index. And that's going to take 13. And then finally, we have our offsets. And that's going to take what? 5. So, ladies and gentlemen, this is our lesson for today. There are other questions there that we could work on, but if the power comes back, I'm going to just push it to you, and then you can just tackle them in your own time and share your answers on the platform so that we see your progress. Thank you for being wonderful people, and despite the ups and downs, you can see that we as tutors are really making the effort to attend these sessions, but it looks like the world has other plans. the world has other plans like ECG. Like this yesterday, ECG had plans on my back. Today too, they are doing the same thing. The other tutors too, ECG has had some plans on them. We've seen that our lessons have been inconsistent, but we are still trying to make it up. Next time we meet, I'll be bringing a past question for DCIT 207. I have really tried getting that for a long time and I've successfully gotten one. So we are going to start tackling the regions that we have covered. And then even the ones we have not covered, we are still going to use it as a foreshadowing to those lessons to come. I wish you all good luck and goodbye, people.
Goodbye, sir.